Today we're going to perform a lab where we're going to try to find, using what we call a current balance, the magnetic field of magnets, okay, the magnetic field strength B of magnets in Tesla. Now, we're using what are horseshoe magnets, but really those amount to kind of twisted bar magnets. What would we expect the magnetic field to be roughly? In the order of magnitude of 10 to the 17, 10 to the minus 5, 10 to the... Yeah, 10 to the minus 1, 10 to the minus 2, probably looking at 10 to the minus 2 for those bar magnets. So if you get something, honestly, if you get something other than 10 to the minus 2, unless it's really, really close to 10 to the minus 2, and then you probably made a mistake. And it's probably as a result of a unit conversion or something like that. Okay, let me tell you how we're going to perform this experiment. The problem, of course, is phrased in the form of a question: what's the magnetic field strength of a particular horseshoe magnet? And we're going to do this by finding the magnetic field strength twice in two different parts by manipulating two different things. Part one is going to look like this. And by the way, this slideshow is up on Google Classroom for you already. So the apparatus is going to look like this. You're going to have a power supply. And that power supply is going to be hooked up to some wires, two wires, in fact. One wire that goes to this thing that we call a current balance that's attached to a retort stand, and one wire is going to allow the current to go through that wire, through one of the arms of that current balance, down into a little printed circuit that has an exposed wire in between this horseshoe magnet. This little thing right here is our little printed circuit. So ultimately what's going to happen is that the electrons are going to go through this wire, they're going to go through this arm of this current balance, they're going to go through the printed circuit, which is exposed to a magnetic field, and then they're going to go back out the other side, back to the power supply. Now that should cause a magnetic force on the wire. We learned about that yesterday, right? We can find the direction of that magnetic force using the hand rule for deflection, and we can find the strength of that magnetic force using an equation that we learned yesterday, F is equal to ILB. There's a force on the wire, but by Newton's third law, we know that if object A applies a force on object B, B applies an equal and opposite force on object A. So if the magnet pushes on the wire, then the wire pushes on the magnet. Now notice the magnet is sitting on a scale. So that means if the magnet is pushed down by the wire or by the magnetic field caused by the wire, then the scale is going to read something as a mass that it thinks is more mass. It isn't really, right? It's really just the magnetic force pushing down on the magnets, but it thinks it's more mass. So that's how we're going to actually measure the magnetic force, is by determining what the scale thinks the mass is, multiplying it by 9.81 to get a force, which will correspond to that magnetic force. Does that make some sense? So it's set up like this. This is already set up for you in the lab here, guys, so you don't need to worry about that. And I'll help you out with it if you need it as well with the apparatus. Now, you want to make sure, just a little bit more specifically with things, you want to make sure that the printed circuit is in the center of the magnetic field. Make sure it's not touching the magnetic field. Make sure the whole part that's horizontal is inside the magnetic field. So you don't want to have it sitting well above the magnetic field. You don't want to have it touching one of the red side or the white side or the bottom in here. You want to have it pretty much centered as much as possible in this magnetic field. Make sure that we zero as well, press tare or the zero button on the scale, even when this bar magnet, or I should say this U-shaped horseshoe magnet apparatus is on there. In other words, we want the scale to think right now when the magnet is on there that there's no mass. And then when the magnetic force pushes down on the magnet, it's going to think that there is a mass there, and that's what we're going to actually record. So place the wire in the center of the magnetic field. You're going to turn the voltage knob, which is this knob right here, okay, the top one, as far to the right as it will go. And then the current knob, which is the second one down here, you're going to turn as far to the left as it will go. And then you turn on the power supply. And of course, the switch for the power supply is down here. At this point, you should see 0.00 for volts, and you should see 0.00 for amps. And there should be no current going through there, and therefore the scale should read 0. If the scale happens to read something other than 0 right now, press the 0 button again, press the tare button again. Until you're actually collecting data, you want it to read 0. All right, next thing you're going to do is manipulate the current, change the current. So you're going to adjust the current knob on the power supply so that you get a higher value of current. Read and record that value. Read and record the mass value. So you can see right here on my scale now it's reading 0.29 grams. Whatever my current is, 0.61 amps, my mass is 0.29 grams. And the wire length I should record as well. By the way, you're going to keep the wire length constant in this, right? Because you're going to manipulate or change the current through this experiment. So there's 8 different wire lengths that you can use. I'm going to suggest to you that you use the longest one for this experiment, for part 1 of this experiment, which is 8.4 centimeters. That's the one that's in there right now. Okay, so for the first couple groups that go in there, you're going to find that the 8.4 centimeter one is in there. You should just leave that in there. Okay, if you're the 3rd group, the 4th group, whatever, if somebody else has put a short one in there in doing something else in this experiment, that's okay. You just probably switch it back to the 8.4 centimeter one. The longer, the better there. Okay, so what do we do now? You're going to repeat this step 4 a minimum of 9 times so that you have 10 different trials with 10 different currents. I want to have a maximum of 2 amps there. So don't go above 2 amps. Okay, just as a safety precaution, we don't want to go above 2 amps there. Okay, and then of course, whatever the mass is, I put mass in quotation marks, right? Because it's not really a mass. It's really a magnetic force, but the scale thinks it's a mass. So whatever the mass or the magnetic force is that corresponds to those 10 different currents. Then you're going to do part 2. Part 2, you're going to have the same setup here, except in part 2, instead of changing the current, you're going to change the length of wire. So what I want you to do is, in this one, change these little printed circuit cartridges, pop them in and out in between trials while keeping the current constant. My suggestion for keeping the current constant would be about 1.0 amp, although if you get it 0.95 amps, that's fine. Or 1.1 amp or whatever, that's fine as long as you record what the value that you used is. The current, though, in this one has to remain constant, and it's the length of the wire that's going to change here. Read and record the length of the wire. Well, the current, first of all, and the length of the wire that you happen to use. Let's say the first one you're using is 8.4 centimeters. What's the mass? 0.29 grams. Change the length of the wire to another one, 4.2 centimeters. Okay, what's the mass that's given to me now on that scale? And so on and so on and so on. Notice there's only 6 trials in this because we only have 6 different cartridges with 6 different lengths of wire. So 10 trials for the first one with 10 different currents. And the second one, you're going to have 6 different lengths of wire corresponding to the 6 different cartridges that we have. And you can imagine what's going to happen, right? We're going to do something with that data and then ultimately plot graphs with it. This is your data from experiment 1, which we've recopied into analysis. This is your data from experiment 2, which we've recopied into an analysis table. This is what the first thing you actually have to do in analysis is calculate the magnetic force. Anybody know how to do that? I'll give you a hint. It's not F is equal to ILB. You're not going to use that. What is it? A times M or M times A, yeah? Or M times G, right? So you're going to say whatever the mass is times 9.81. But you do want to make sure that your mass has been converted to kilograms before you multiply it by 9.81. So if it's measured in grams, divide it by 1,000 and then multiply it by 9.81 and complete the table with magnetic force. Same deal over here. Just take your mass in kilograms, multiply it by 9.81 to get the magnetic force. And then you're going to plot 2 graphs. The first one is going to be force versus current. It should be a straight line. Okay, it should be a very good straight line. In fact, if you don't get a very good straight line, you've messed up on this because this works out really well. Okay, there's no ambiguity towards this one. And you, of course, you know what to do with this, right? You know what to do with this. y is equal to mx plus b. I'm not going to go through that process with you today, okay? I'm going to remind you that you're going to use the process y equals mx plus b, and I'll remind you that the b, the y-intercept, will be either 0 or very close to 0, so you can ignore that. And then figure out what the slope means. Okay, what does the slope mean? Okay, and what's the value of the slope that comes from the graph? And then from that, you're going to determine the value of the magnetic field strength. I can help you with that if you struggle with it over the next day or two, but I want you to give it a try yourself. We've done that a number of times now, and at some point, you're going to have to be able to analyze a graph that you've never seen before. So let's try it here, and then if you struggle with it, let me know. So find the magnetic field from your force versus current graph. Make sure you put a title in there as well. Next one you're going to plot is force versus wire length. It should also be a straight line. It should also be represented by the equation y equals mx plus b. The y-intercept here should also be either 0 or very close to 0. Do your thing with y equals mx plus b here and find the value of the magnetic field that was used. So now you've got two magnetic fields. The magnetic field of the magnet from the first experiment and of the magnet from the second experiment, which is the same magnet, right? So it should be theoretically the same value. What I want you to do at that point is just average the two together. Average the value you got in number 1 with the value that you got in number 2. And that's going to be the magnetic field strength that you're going to conclude the magnet has. Now, just a little like common sense note here, right? If you get two dramatically different numbers, you've made a mistake. Right? If you get different orders of magnitude, you've made a mistake. These won't come out to be exactly the same, but they should come out to be good. They should come out to be fairly close to the same. So you might get 0.7 and 0.8. Like those are okay. Right? But if you get 0.7 and 0.1, you've made a mistake. Does that make sense? They should be relatively close together. And like we said, they should probably be in the order of 10 to the minus 2. So it'd be more like 0.07 and 0.08 as opposed to 0.7 and 0.8. And then your conclusion, what is the magnetic field strength of this bar magnet? And then how do you know? That's a pretty easy. That's a pretty easy how do you know, right? You did your analysis with the two graphs, you averaged them together, this is what you got. And then, of course, your sources of error. 2 or 3 good sources of error, and then suggestions for improvement, as always. What do you got to hand in for this? Well, we're going to start with your data, okay, which is 2 sets of data, right? 2 sets of data. We've got current and wire length, current and mass. And then we've got wire length and mass. And then, of course, we've got our analysis, which includes 2 more tables, and then 2 graphs, and then the y equals mx plus b thing with your graph. And then, of course, you've got your conclusion, and you've got your sources of error, and that's it.